Okay, let's continue with the next topic. Okay, we have discussed the swing equation, right? This is the equation that describe the response of the synchronous machine, right? We are expressing the relationship between the rotation of machine, okay, with the response of the power output, right? You can see that the rotor angle equation here, we call this swing equation, and on the right side it is the difference between mechanical power input and the electrical power output. So you can see that when the machine operates steadily, or it is in the steady operating condition, right? This term would be zero, okay, because there is no acceleration. Last time we saw that when the Pm is greater than Pe, okay, meaning that you give too much input, right? Too much mechanical power input, right? That means that the machine is going to be accelerated, and if PE is less than PM, okay, meaning that the load is less than, sorry, if the load is greater than the input, okay, that means that the machine is going to be decelerated, okay. So at the equilibrium at the constant speed, so you can see that the Pm is equal to Pe. This is at the steady state or steady operation, the constant speed. Okay, so the acceleration is zero. Okay, and as we said, Pm is greater than Pe is acceleration, right? So this kind of expression, you can see that we have to express this in terms of per unit with respect to the rating of the machine. Okay, and last time we derived that the inertia constant, right? The inertia constant is, or we call per unit inertia constant. Okay, this is a fixed parameter of the machine, okay, with respect to the size of the machine itself. So the swing equation can be written in terms of h divided by pi f0. F0 is the synchronous frequency or system frequency. It can be 50 hertz or 60 hertz, for example. Where in this case, you see, when you have the pi here, so the radian, I mean the rotor angle is expressed in terms of radian, or if you have 180 degree at the numerator denominator, right? At the 180 degree at the at the numerator, denominator, sorry, denominator. So this is the angle is in degree, right? So now it's clear, okay? So the equation, everything is written in terms of per unit. So you remember from last class that the quantity that are of our interest are the rotor angle, delta, okay? This is the rotor angle, and the other one we call omega, okay. We are of interested whether the system will, I mean, if we know that the machine is decelerating, so we want to know somehow, right? You want to know the speed of the rotor as well. So the omega is the angular speed or rotor speed, okay, which is the alpha, the delta by dt, okay, the delta by dt. So in this lecture, okay, in this section, we are going to try to model the generator for stability study. Okay, last time we did this one, right? You still remember that we introduced the disturbance. For example, in case of last time, the disturbance was that we reduced the electrical power output, right? Last time We reduce the electrical power output by from nominal value to 200, for example. So this is the disturbance is here in the PE. Okay, we have introduced this disturbance in PE. Okay, so we are interested how the PE, okay, would be associated with the rotor angle. Okay, okay. If we change the rotor angle, you learn from power system one that the electrical power output would change. Okay, that was very easy, right? Without any needs to do any derivation. Still remember last class from power system one that we have E, and we have for example here we have another line. This is V, right? You still remember what the power transfer between the two buses? I have derived this for several times. The power transfer between the E to V, right? This is EV upon X sine of the angle difference. So if we put one of the voltage here as a reference, the terminal could be the terminal voltage. Okay, this is it should be here. It's terminal voltage. Okay, this is the X of the machine. This is the, so for example, we discussed XD, right? So the E and the angle of delta, this is the power angle, right? This is the XD over here. This is power transfer from the machine. Okay, so we try to do this in an appropriate form. Okay, we are trying to model the power transfer or PE, right? We are trying to determine the relationship of electrical power in terms of the rotor angle, right? So you can see that if we say if it's supplying, if the generator supplying electrical power um, through the line, right, with the impedance CL, and it could be the shunt impedance connected to the generator terminal. Okay, this could be for the for the sake of compensation for whatever, right? For example, we have a CS connected in series like this at the terminal of the generator, right? This is the terminal of the generator terminal. Okay, so now we try to model this. We apply the classical model as a constant voltage source behind direct axis suppression reactant, traction reactance. This is the what do we mean by this one? A classical model, and the saliency is signal. Okay, meaning that we consider just the round rotor case. Okay. Um, if we connect this generator to infinite bus, okay, what does it mean by infinite bus? Okay, normally infinite bus is used to model the large scale power system. The property of infinite bus are as follow. You see, we have the whenever there is we call the last system. Okay, the infinite bus will have the this following property with the constant voltage, constant frequency, constant angle, and infinite inertia. So, I mean, to put it in a simple term, okay, infinite bus is a huge system in which whatever you do with this system, okay, you can't even change anything in the system. Okay, so you imagine, you see, you have two bowls of water. Maybe this is a huge one. Okay, 1,000 liter, for example, and you have a small glass like this, maybe 250 cc. Okay, and you're trying to this 1,000 liter tank is filled with clean water. Okay, for example, this is clean water, and you have a small cup full with the water with mud. Okay, we are trying to pour the mud into this okay, a huge tank. All right. So you can see that there is a, you know, you can't even contaminate the clean water in such a big tank. So we can say that, you know, whatever you have with the smaller one, well, I mean with the small glass, right? You put it into the bigger tank, you can't even change the purity of the entire tank, for example. So we can say that this is just one analogy, right? Or this is I hope this is clear. Infinite bus, okay? So we can why are we interested in modeling this system as an infinite bus? Because we want to just see the behavior of the generator itself, okay? So we don't want to, you know, disturb the relationship on the generator side. So we just fix this as a huge system. So whatever um, you do with the system, it doesn't have any impact on both sides, right? So um, now we try to model. So we want to find the relationship between the E dat. E dat here is the internal EMF, right? So this is where we have the rotor angle. So we want to see the effect of this rotor angle to the PE. Okay, we want to see these two relationship. Okay, so we modeled the E and V. V is the terminal voltage at this point. So um, we are trying to convert this box, right? Because this box is connected in star, because this is a neutral. Okay, we see that the generator terminal is the neutral of this connection. So we transform this into delta. Why is it delta? Because, you know, we want to connect one end to the ground. Okay, so this is the connection like this, and this is to the ground. Okay, this is the delta. So it's very simple, right? We transform star to delta. Okay, by this the approach we learned it already, right? In this case, we want to have star the delta like this. So what do? We have right, the transformation like this. Okay, I hope you can do this one yourself, right? Um, so we transform this, and we formulate this in terms of wine. Okay, so it is the multiplication. Okay, the j x d prime times cs. Okay, the multiplication of everything divided by the z load. Okay, and we have the inverse. So we get y10. Y10 is here. This is one, terminal 1 here. Okay, terminal 1, y1. So basically the C, okay, it's the product, right? The sum of all the products divided by the CL. Okay, this is the impedance in the opposite to this this is Z10, and we just reverse this to Y. Okay, this is in terms of admittance. Okay, so you have the transformation. Once you have the transformation, you want to see the current in the two ports, meaning that this is the current at the sending end and the current at the receiving end. Okay, the current injection at both ends. Okay, so we see that the current being injected to the left side, which is the sending end or internal EMF. Okay, is the y10 times e prime. This is this current here. Okay, y10 e prime. This is the current, and the current flowing from e prime to v. So it is the e prime minus v times y12, right? So we just rewrite this two because the I1 is the sum of these two. All right. Similarly, you see I2 is the you put the KCL at this node V. Okay, so you have this current is V times Y2 0. Okay, and the sum of this guy it is I2 plus this guy is equal to the current exiting this V node. Okay, so you rearrange this I2. So you can see that this is just a normal I mean the network equation in terms of current injection and the voltage. Okay, so this is the normal bus admittance matrix. Okay, the bus admittance matrix, you learned it already, that the diagonal elements of this matrix is the sum of all the admittances connected to that bus. Okay, where the off diagonal, or for example y12 or y21, is the negative value of the admittance connected between the bus ij. For example, in this case, this is bus 1, 2. Okay. Now you can see that if you want to express the PE, okay, PE is the, remember, PE is the electrical power output from the generator. Okay, so the PE itself is defined by the real part of the complex power. Okay, this is the real part of the complex power exceeding from the generator. Okay, so you can see that the PE is the real part of the product between the complex phasor of E prime times the conjugate of I1. Okay, you can now we substitute everything. We substitute the E prime. Okay, we substitute the phasor of the EMF plus the current. Okay, the current I1 expressed in terms of admittance. I mean at the elements of bus admittance matrix. Now you rearrange everything, and we made a certain assumption. Okay, we made the assumption is in that, you know, the resistance are all neglected. Resistance of the lines are all neglected. So the theta 1 1 and theta 1 2, which is the anchor of, you see, this is the anchor of bus admittance matrix, right? Y11 and theta. It means that if you neglect the resistance, so you just get the imaginary part, or the angle is 90 degree, and y12 is 1 over x12, right? We just put the all these assumptions in the equation PE here, so you get this E times V times x12 times sine of delta. So x12 is the reactance between the equivalent reactance, right, between bus 1 2. Okay, this is the reactance between bus 1 2, because you can get just this guy, right, y12, and you get the reverse of this, you get the division by x12. So now you can see that when we express the relationship, right, you can between, this is just like you have the flow from bus 1 to bus 2. Okay, so the impedance of x12 would you know, include everything inside these three elements. Okay, this is the PE. So now you can see that when we model the PE in stability analysis, we use this kind of relationship. Okay, and you can see that the plot of the PE, you see that at any instance of the along this curve, we plot between PE and delta. Now you see that the maximum angle, right, of the delta, which is possible, we get the maximum power of EV times x divided by x12. Okay, this is the maximum power transfer between the generator to the load, to the infinite bus. Okay, and this somehow, you know, it might be called the stability limit of power systems, because, you know, why is it a stability? Because um, if you increase the delta, right? Just like what does it mean by increasing the delta? Means that your rotor speed will, okay, will differ from the synchronous rotating frame, right? Meaning that you try to insert additional power, but you get less electrical power output, right? If you increase the delta beyond this point, meaning that you push harder but you get less. Okay, that's why it is not stable, it is unstable. Okay, so this is somehow, this is what we call this stability limit. So we see this example 11.1, right? So the problem says that you have the parameter, you have a synchronous twin machine with these parameters xd, xq, xd prime. So we are interested, of course, during the transient, right? So we put the xd prime as our parameter. Okay, we neglect the armature resistance. The machine is connected to infinite bus with voltage of 1.0 pu. So you just draw this. It is an infinite bus 1.10 and the anchor of 0. Okay, and the generator is delivering. This is a generator xd prime. Okay, and the generator is delivering real power P of 0.5 pu and the power factor of 0.8 lagging, meaning that 0.8 lagging, so you can find the S, okay, because P divided by S is the power factor, right? So you therefore the S or apparent power of this is 0.5 divided by 0.8, okay, this is the apparent power, okay, MVA, okay. This is power factor of 0.8 definition of this, okay, and the problem asks you to determine the voltage behind transient reactance. So this is E prime, and the power and the transient power angle equation. So PE, right? PE itself is EV upon E prime. This is the transient power E prime times V divided by X. In this case, it is connected directly to from the generator to the infinite bus, right? Without having the line or the shunt impedance. So you have this XD prime because this is in the in the transient period and sign of delta. So the delta has to be defined, right? Has defined as the power angle of the machine, right? Now you see that now this is not angle of 0 because why is it so? Is it oh yes, this is an angle of 0. Now in order to determine this E prime, right? Now you can use the equation. You see that is the current will flow from the internal EMF to the generator, I mean to the terminal, which is connected now to the infinite bus, right? So you can say that the E prime is equal to V at the terminal, V at infinite bus plus, right, the current times J X D prime. Okay, now the voltage at the infinite bus is given as a reference. Also, this is one per unit. We can see this is at 1 per unit, and the JXD prime is known because this is what, this is J 0.3, J 0.3. So the only thing left is the current, right? You have to determine the current. So the current is can be defined, that can be computed from the loading condition, right? So the loading condition, once you know the S and you know the V, now you know S, you know V at the terminal, okay, at the load point, okay, you know these two, you know V and you know S, so you can find I in this case. So the I, if you work in terms of per unit, you have the S conjugate divided by V conjugate. So you have this much. So you put this into the equation, you find the E, and this is the E and the power angle. Therefore, you just take the magnitude of E, right, which is 1.1226 times 1 divided by 0.3 sine delta. This is the transient power angle equation. Okay, this is this is an example how to find the power PE, right? Electrical power in terms of the rotor angle. All right, 11.6. You see that the machine 60 Hertz synchronous machine has a transient reactance of 0.2 per unit, and the inertia H. Okay, this is H in this case 5.66 megajoule per MVA. So this is, you can see that this is the normalized with respect to the rating because divided by MVA. Okay, the generator is connected to infinite bus through transformer and double circuit transmission line. So there is a transformer and two double circuit line connected with the infinite bus on this side. This is infinite bus, right? If the resistance are all neglected, reactance are expressed in terms of per unit based on common MVA and marked on diagram. The generator is delivering real power of 0.77 per unit to bus 1. So the P delivering to bus 1 in this case is the 0.77 pu, okay, to bus 1. The voltage magnitude of this, okay, the voltage magnitude at bus 1 is 1.1. The infinite bus is 1.0. Okay, this is clear because the voltage in this case is greater than the voltage in bus 2. Therefore, the power just flow from bus 1 to 2, right? So the problem asks you to determine the generator excitation and obtain the swing equation as per the previous problem. So just obtain the swing equation, or I guess this is in terms of PE, right? Oh, swing equation, sorry, swing equation. So you have to put the whole things into the swing, okay? Now you can see that how to start with this guy. Okay, let's see how we can do this one. Well, you can define the relationship, right? For this, you can see that you can determine the voltage. I mean, you can determine the power angle for this case of the bus 1. First, we have defined this the power angle at this bus 1, delta 1 here first, because the power supplied to bus 1, this is an input to bus 1, is 0.77 per unit, which means that the 0.77 per unit also, 0.77 per unit will flow on the transmission line, these two transmission line, right? Or double circuit, okay? The 0.77 per pu will flow over this corridor, okay? The sum of this will flow 0.77 pu. Now you know that the power flows from bus 1 to bus 2. The angle, the V here is 1.0, and the angle of 0. So now you can determine the power angle of bus 1, and soon after you know the power of bus 1, we could map back to the delta here, right? So you determine the delta 1, okay? Delta 1 can be defined by 0.77 and V1 1.1, V2 1 per unit divided by 0.4, because these are the parallel of the point 0.8 and 0.8. So after the parallel of these two, we get 0.4. Okay. Now you get the angle of delta 1 of bus 1, 16.26. 16.26. Now what can we do next? Okay, we determine the current. So we know the current. So after you know the current, okay, you can map the relationship, right, between this and the voltage here. Okay, you know the current because what? Because the angle difference between these two, right? The current flowing from 1 to, it's what? It's just V1 minus V2, right? Divided by X12. In this case, X12 would be your J.4, right? V1 is what? It is 1.1 angle 16.26 divided by 1 angle of 0 divided by J.4. Now you know this current, okay? Soon after knowing this current, okay, this current is the same as this current because you know this is the series circuit, right? Now you see that you can determine the current, okay, the current for along this I mean flowing through the corridor from bus 1 to 2. You get this I, and now you can find the E, right? Soon after you know the I12 is this guy here, right? 0.7826, the angle of negative 10.305 per unit. Now you can find the E, right? In this case, the E prime is the, okay, is V in this case plus J times I, right? I'm sorry, this is I in complex times J, the sum of all the impedances. So you have J.2, which is the transient reactance, plus 0.158, right? So you find the E prime here from the known V, then the total current I, right? And plus the reactance here, 0.4, right? That's why you can this is how you can find the E prime. All right. So you find the E prime to 1.25 angle of 27.819, right? This is E prime. So now you can determine the swing equation. Okay, the swing equation, if you write in terms of the angle of radian, so you have 60 hertz f0, and you have the h. Okay, h is given 5.66, right? And the PM, this is PM minus PE, right? So PM is 0.77. PM is 0.77 because the generator delivers 0.77 per unit to bus bar 1. Okay, this is so if this runs steadily, meaning that the PM is equal to PE, right? So you see that the PM before the disturbance, PM and the PE should be equal, right? So the PM is 0.77 minus PE. So the PE itself is PE is EV times the total impedance. Okay, this is the total impedance of this guy. So this is the, I don't know how much, 0.6 plus 0.158, so you have 0.758, right? E, you substitute E by E, your E should be 1.12, 1.2, 1.1226 into 1 sine delta, right? This is PE. Okay, this is okay. So this is the swing equation. All right. Okay, now we are ready uh, to analyze the first type of stability. We have discussed everything needed for the analysis, right? So we are now going to start analyzing the two types of uh, rotor angle stability, namely the small disturbance and the large disturbance, right? So we start with the small disturbance, or we call steady state stability, or we call dynamic stability. Okay, if you still remember, we have just discussed this from this chart, right? We are going to in this chapter we are discussing just the rotor angle stability. So we have two types of classification based on the scale of disturbance, right? We have the small disturbance and large disturbance. In this case, this is the dynamic stability. Okay, so in this lecture we are going to focus on these two types, and during this dynamic stability, so we have to deal with the oscillation, and right, so right, we have to handle with the oscillations. Okay, now we are going to define, right, what do we mean by the small disturbance. As we discussed earlier, that the small disturbance is as the name suggests, right, it is small. For example, we have some load changes, right? We have some shift of the rotor angle, a little bit shift of the rotor angle. All right. If the disturbance is small, the method of analysis can be linearized, as we discussed earlier, right? We know that the equation itself is nonlinear. So you see from the swing equation itself, we have the swing equation at this, okay, like this, and we have discussed that the PE is the oscillating sinusoidal, okay, because the independent variable is delta, and PE is EV upon X sine of delta. Okay, so the PE is not constant, okay, but it's changing over with the function of the rotor angle itself. So you can see that if the disturbance is small, for example, we assume a small disturbance, we change the rotor angle a little bit by changing by introducing the small rotor angle, small change in the rotor angle. Okay, you can see that the equilibrium point, right, of the system will also change. Okay, if we assume that the delta change a little bit from the initial value of delta 0, this is the initial. Okay, we assume the a small disturbance, the change of delta. Okay, now we put this change, and we assume the linearization. We put the linearization, right? Now the delta is changed. Okay, the delta has been changed. Now we do the linearization on the, I mean, on this equation, right? Now you see that the sine, this has been not linearized, but we just expand the term, right? We have the second derivative of delta 0 plus delta, so we can split into two terms. We have sine of the sum of the angle, so you have sine cos plus cosine. Okay, sine cos plus cosine. We just expand the term, and we have used the trig identity. We approximate, right, the cosine term, cosine of a small angle, because we assume that the disturbance is small, right? This is small. By stating that it's small, so cosine of a small angle is close to 1, and the sine of a small angle is approximately the same as the angle itself. So we change the right side of the equation. Okay, wherever we have cosine, we substitute by 1. So this is becomes 1. And the sine of delta delta, this is delta delta itself. Okay, so we have, this is after the approximation. This line is after the approximation. Now you can split the two terms, right? You can see that from the right side of this equation we have, okay, we have this term, okay, Pm minus P max sine of delta 0, and on the left side you have this h divided by f0 and d squared, the second derivative of the initial angle. So these two is what? It is a swing equation at the initial operating point, okay? Because the angle itself is a function of delta 0. Okay, this is delta 0. And the second term, okay, the rest term, the second term here, the green one, okay, the green one is the linearization swing equation. This is due to the change. You can see that this is due to the change of delta delta. Okay, because these two, the two terms in the terms in the green are the function of, is a function of delta delta. Alright, so this is the this is the equation that describe the dynamics of the rotor angle due to the change of the small angle delta delta. Okay, this is initial, before initial operating point means before disturbance. Okay, this is the effect of the disturbance itself, because this is the effect of the disturbance. Okay, so in summary, right, after the introduction of the disturbance or the small change in delta, the response is like this. The response is the linear sum of the initial response plus the effect due to the disturbance itself. All right, now we can analyze the second term, the second equation, or linearize the swing equation. You can introduce the synchronizing coefficient, okay, PS in this case, because what? Why is the synchronized coefficient? Because you can see that this is the linear, I mean the second order ODE, right? Now, if you learn from circuit and other classes that when you have second order ODE, right, that is a chance, or not that is a chance, there is an oscillation, right, associated with the second order ODE. So if you have appropriate damping, right, the ODE will reach, I mean the response will reach the steady state without any oscillations. Okay, so this term, the second derivative, would create the oscillation. So you need somehow, you need some terms to damp it. Okay, so if we define, right, the PS is equal to derivative of P with respect to the delta. Remember, P is P max, right, sine of delta. So derivative of P dP by the delta is P max cosine of delta, right? And we substitute this by delta 0 because this is the at the term, delta 0 is at the initial condition. So this guy, it would become this, okay, P max cosine. So this term is what we call synchronizing coefficient. So we substitute, if we substitute this by PS, right, and we get the second order differential equation with the natural frequency of oscillation, like this is the natural frequency omega n, right, at this, and you can get the root, right, and you define the natural frequency of oscillation. So you have to deal with the damping somehow. Okay, we have the deal with the damping, right? If you don't have the damping term, this guy, the linear, the swing equation doesn't go smooth to the steady state, right? The steady state is not smooth. So we introduce the damping coefficient somehow. The we put the damping term in this case d times delta delta differential of right d by dt of the delta delta. Okay, now this becomes the standard uh, second order ODE with the damping ratio and the natural frequency, right? If you have just this equation, right, there is no possibility of this second. I mean, this system will be undamped, right? So we just put the damping power, the this term into the equation, right? So we have to deal with this damping ratio and the natural frequency. So if damping is exactly the same as the natural frequency, so this is the case of critically damped, right? And if the damping ratio is greater than the natural frequency, this is the overdamp, and in the other case, right, where damping is less than the natural frequency, you get the underdamped case. Okay, this is what you have already learned, right, from other classes. Okay, so you have to deal with the the characteristic equation. We determine the characteristic equation, and the characteristic equation will tell you what kind of damping it is, depending upon the root of this equation. So you have, if you have the zero root, means that it's critically damped, and if you have two different positive real roots, right, meaning that this term, right, is greater than the rest term, you get overdamp. And if you have sorry, this you check from this guy, the square root here, right? Critically damped means that this essentially this is critically damped means 1 minus eta square is 0. Okay, so this is critically, so you get just one real root, right? And if this guy is greater than 0, you get two different positive real roots. So this is, if you learn from control theory, this is the eigenvalue, right? Okay, and if you get the complex number, right, you get the underdamped case. Okay, this is how we define the damp frequency of oscillations. Okay, now we have dealt with the equations from the second order point of view, second order ODE point of view. Now there is another possibility that you can handle this kind of equation if you learn from control theory, right? The second order ODE can be dealt with by the state variable form, right? This state variable form is used, to transform the second order equation to first order. Okay, if we define the state variable as the delta delta, this is the change of the rotor angle, right? The derivative of this guy, the derivative of x1, we define it as an x2. So the derivative of x1, you will get d of delta delta d by dt, right? The time differential of the angle difference. Okay, now you can rewrite the equation, this equation into two. I mean, you can rewrite the the second order ODE into two first order ODE in this form, right? X1 and x1 dot and x2 dot. Okay, and x1 dot is the x2, right? X1 dot is X2 because we define that the X2, this is definition. The first line is the definition. We define X1 as delta delta, and X2 is delta omega. Now, this is the, what is delta omega? This is the rotor speed, right? The change of rotor speed. Okay, this is the change of, this is the change of rotor angle, but in this case this is the disturbance. This is the change of rotor speed. Okay, now you can rewrite this second order into this form, and you write this in terms of the matrix. Now you have x1 is equal to x2, x2 dot, right? X2 dot is x2 dot is d by this guy here, right? So you can just rewrite the equation, you can recheck it, you get this kind of matrix. Okay, this matrix. This metric is unforced state variable. Unforced means that there is no input term. Okay, there is no input term. So typically we have x dot is equal to ax plus bu. Okay, in terms of unforced state variable means that there is no input here. So b is 0. Okay, we have for the unforced we have the coefficient matrix of this guy a. Okay, and the output vector. So the state variable form, it's an x dot equal to ax plus bu, and y, which is the output variable, output, right? Output variable is cx plus du, right? So in this case, our output is the x1 and x2 itself, because the output is the variable of our interest. Okay, in our case, we are interested in x1 and x2, which is the rotor, the change of the rotor angle itself, and the change of the rotor speed. Okay, meaning that if you know the initial rotor angle delta 0, right? Soon after you introduce the change, of course, because this is an input, you have to plus the delta, and you get delta at any time t. Okay, and the omega, if you know the omega naught, right? You determine, this is an output, right? You determine the delta omega. Now you get you get the rotor speed at time t. All right, this is an output. So in this case, you have learned it already. You have the state variable form, right? Now we want to determine the transfer function. The transfer function is the relationship between output and input, right? Because output divided by input is a transfer function. Okay, this is a transfer function. Why is this transfer function? Because you multiply input by transfer function, you get output in S domain, right? Now you can play around. Okay, you have xt, x dot is equal to ax, right? And we take the Laplace transform on both sides of the equation. So the left side is the Laplace of first derivative. You get s and xs minus x0. This is this is the normal Laplace transform, and you take the Laplace transform on the right. Okay, then you find the xs. Okay, is this matrix si minus a inverse times x0. Okay, this is an xs. Okay, that means that this is the more or less like this is it no, I shouldn't say this is the transfer function. Sorry, this is not a transfer function, because we don't we didn't apply anything as an it can be a transfer function in a way, because this is an output variable. X is an output, so it is right. It is a transfer function, of course, but it's not so big deal how we call it, right? But we want to solve this this system will require this system, okay, because we don't have this b term, okay, and the y and x is the same, okay, so you can call this as an in, x as an in and y as an output, okay. But anyway, we just try to solve this equation. You get xs, which is the state variable in S domain, and now you can, you remember xs, you have delta and delta omega. This is in a matrix form, and in this case you have, right, x0 you have delta 0 and omega 0, and omega 0, delta delta omega, right? Now you can multiply this term, okay, you just multiply the matrix and the vector. This is a linear sum and divided by the same term. Now you can see that the delta and the delta omega in S domain can be divided by these two equations. Now we are not interested in the S domain terms, right? We just need to take the inverse Laplace to this guy, okay? To take inverse Laplace. How to do this is, it's not in this class, right? You can just expand this and using the partial fraction, and right, it's a partial fraction term. Okay, you take the inverse Laplace, so you get the delta and delta omega in time domain. This is in time domain. Okay, and also in this case we have the omega n and omega d. Omega n would stands for natural frequency, and the omega d would stands for the damping frequency. Okay. So we have the expression of the rotor angle, right? This is the change of the delta delta, right? And delta, I mean the rotor angle at any time t can be divided by the initial value, right? This is the change of the delta delta. The incremental change of the delta delta. This is the change of the delta omega. This is the change in rotor speed, right? And so the rotor speed at any time t can be divided by the initial rotor speed minus, right, the term due to the change. This is the term due to the change of the rotor speed, okay. And the time constant, right, is a time constant. How fast this change, right? How fast the change is, okay, defined by the time constant and the settling time. Okay, we have damping ratio, natural frequency, and everything. Okay, now we see the notes. As the h increase, the natural frequency and the damping ratio will decrease. This is of course because you see, when you increase the h increase, so h would increase, the damping ratio will decrease, right? The damping ratio and the natural frequency will decrease. So that will result in the longer settling time, okay? And the increase in PS results in the increase in natural frequency and the damping ratio, the synchronizing coefficient, right? If you change if you increase the synchronizing coefficient, okay, the damping ratio will decrease. Let's see the example, okay? How we analyze. You would realize what we understand, what does it mean by the small signal stability. This is probably like the previous example. We have a synchronous machine having inertia of 9.94, and the reactance of the transient reactance is 0.3 per unit, connected to infinite bus to purely reactive circuit. Purely reactive means we don't have resistance. Reactants are marked on the common base, so we don't need to change anything. The generator is delivering 6 pu at 0.8 pf lagging to infinite bus of v, then the angle of course of the infinite bus is v and the angle here is 0. Okay, assume that the per unit damping coefficient, the damping coefficient of the generator, right, is 0.138 per unit. Okay, 1.138, and we assume the small disturbance of 10 degree electrical degree, or it is equivalent to 0.1745 radian, right? And for example, the circuit breakers open quickly. Obtain the equation that describes the motion of the rotor angle. Okay, the motion of the rotor angle. That means that the rotor angle is delta. So this is the equation that explains the motion of rotor angle. That means that we need to find the delta at the time t and the generator frequency. Okay, the generator frequency. All right. Uh, it's just the same idea, right? We need to from the problem itself, the first part of the problem, we need to somehow, analyze the E, right? You have to find the E first, okay? The excitation, because this is the place where you can define the initial operating point of the system, right? This is the initial point of the generator, right? This is the step we have discussed it already, right? Okay, we starting from defining the the complex power, right? We find the complex power. Actually, this is not apparent power. We should say this is the complex power. You have to change this, because apparent power, if it is apparent power, we are interested in just the absolute or the magnitude of the power itself, right? But in this case, we put the angle, so it should be complex power. Okay, the current, we find the current, and then we find the excitation, right? Now we can find, in this case, we find the the initial delta zero. So now that you know the delta zero, you know the synchronizing torque, right? Or the synchronizing coefficient. Okay, synchronizing coefficient is P max times cosine the delta zero. This is the initial angle, right? This is the torque. If it is the from the physical meaning of this synchronizing torque, is the torque that the machine, right, push to synchronize itself, or use to intact itself, to keep this to keep the generator intact to the system. So there must be some force that hinge this generator to the rotating system. Okay, so PS is, of course, this is the divided by P max cosine zero. P max is EV upon X. Okay, we supply the power from machine. Now it is in the internal EMF to the infinite bus itself. Okay, so we find the E times V. E is 1.35, V is 1 per unit, divided by, so the transfer impedance between these 2 points, okay, between E and V, is the sum of all the reactances, the transfer reactance, right? This is 0.65, right, times the cosine of the angle, the initial rotor angle, 16.79. So the PS is 1.9884, okay, 1.9884 pu, of course, right? Now we see the damp. Okay, the omega m is the natural frequency first. It is square root from the formula itself, square root pi f0 divided by hps. So you have the frequency of 6.14 radian per second. Okay, and the damping is 0.2131. Okay, 0.2131. Now we analyze the the force-free equation. Okay, this is the equation from this equation itself. Okay, we analyze the second order equation here. Okay, now we analyze the equation. We plug in all the known quantities, right? We plug in the quantities. Now you see that this from this equation, okay, we have the angular frequency. Frequency of the oscillation is the 6 radian per second. 6 radian per second, the damping of 6, and natural frequency of 6.14. It means that it's under damped somehow, right? The damping is less than the natural frequency. So the corresponding damp oscillation is 6 divided by 2 pi. You convert this the damping into hertz. Okay, we change this 6 radian per second into hertz. All right. Now we just plug this in to the equation. You can see that the change, right? Now you see everything. Okay, you see the delta omega. Okay, you plug in all the known quantities. You give everything. So the motion of the rotor relative to the electrical degree and the frequency excursion. The frequency excursion can be defined from this equation itself. Okay, now you see this is the equation that describes the change over time of the rotor angle and the frequency itself. All right, so this is the time response. Okay, so the initial condition of this is at the time 0. Okay, and once there is a disturbance, means that we change the rotor angle by a certain degree. In this case it was 10 degree, right? The rotor angle would change like this. Okay, and it goes to another steady state at this point. Okay, and when we change the rotor angle, it's also changed the frequency. You can see that but now when once it reached the equilibrium point, the frequency returns back to the normal operating condition. Because what? Because if you see from the eigenvalue of this matrix itself, you see that the eigen uh, is positive, right? It's a complex with the in the open left half plane, right? Because the real part of the eigenvalues are on the left half plane. So this is a stable case. Okay, this is what we learned. Okay, from the small signal stability in the case of you change the delta. Now we introduce another type of disturbance. For example, we introduce the change of the power input. Okay, this is another type of disturbance. It's disturbance number 2, I would say. Now, last time, last example, we introduced the change to the state variable itself, delta delta, right? That's why the previous example it was an unforced oscillation. We say this is unforced because there is no input. Okay, but now we introduce, because on the right side of this equation it was power, right? You remember from the swing equation, right side of the swing equation is power. If we introduce any change to power, it means that we introduce the change to the input term. Okay. Now, if we change the input delta p, okay, what you can do is that we have to remodel the state variable form. Okay. Now you can see that we have introduced the term delta U, okay, because U is input. Remember, U is input in the state space representation, right? Now you introduce the change to this equation. That's why we have to include this delta U in the steady state in the state equation. You remember, you see that the A part is remains the same. Okay, we introduced to the delta U. Now we have to take the Laplace transform to the force state variable equation. You can see we have force state variable equation. We take the Laplace to the both sides of the equation, right? Now you can see that the change of soon after the transform, right? Now you see that the change in delta delta, the change in the rotor angle and the rotor speed is is affected by the change in the delta U itself. Okay, so we introduce the change in the power. It would change the rotor angle and the rotor speed. Okay, and once you have this, you take the inverse Laplace, so you have the time domain expression of the change in delta delta and delta omega due to the change in delta U in this case. All right, this is the change, okay, of the force steady state I mean the force state variable equation, right? This is the to incorporate the change of the delta P. In this case, you have to, I think you should highlight this one. This is the difference, right? This is the change of the power. Okay, we have to introduce the change in the power, and this is the corresponding change of the rotor angle and the rotor speed. Okay, now we see the example. All right, you can see that the example remains the same. The generator used to operate at the initial angle of 16.79. When an input power is increased by a small amount, it's increased by 0.2 per unit. Of course, this is the force response, right? You change the power input. The generator excitation and the infinite bus bar are the same as before, which is the 1.35 and the V is 1 per unit. So we use the equation has been derived, right? We use this is the equation, the response, or the response in this case we change the power a little bit, right? We change the power a little bit, so the U is here is the step response, right? This is, we put the unit step with the magnitude of 0.2 per unit. Okay, the magnitude of 0.2 per unit. So in this case, the problem is that we obtain the step response of the rotor angle and the generator frequency. Of course, somehow, you know, uh, the frequency, okay, it's derived from the rotor speed, right? You change the rotor speed from radian per second to change this to hertz. That would becomes the frequency. Okay, I'm not sure whether you understand this or not. Okay, why the first problem we also discussed the frequency, right? Frequency is a result when you determine the omega first, right? Because the omega is radian per second, and you change this the omega, okay? This is a rotor angle with respect to the rotating frames, right? The synchronous rotating frame, you remember, okay? Therefore, the rotor speed is relative to the synchronous speed itself. Okay, that's why, you know, when you find if you when you find the omega, you can, you know, transform this into to the frequency. Okay, now it's clear, right? you just, in this case, you just substitute the value into the equation. Okay, now you see that this is the response of the rotor angle due to the change or the step change of the delta p of 0.2 per unit. You change the 0.2 per unit, and this is the time excursion of the rotor angle. And also this is the change of the frequency. Okay, and the problem, I mean, the question B and C are just, you know, the plot, the MATLAB plot to see the time response. Okay, now you can see this is the equation, and you see that is an initial operating condition, right? At the given initial point of 16.79, this is 16.79 due to before the disturbance, and once we introduce the change in power, right? When we change the power, there is a rotor excursion, the change in the rotor angle, and it would reach the final steady state. I mean the steady state at the new equilibrium point. This is the new equilibrium point after the load increase. Okay, that would make sense, you see, because when we increase the angle, right, meaning that the power transfer P is equal to EV times X sine delta. When once you increase the load, because the load change, right, the input power increase. Okay, so this is increased, so the your delta is increased as well. Okay, because this just like, you know, the generator has to put to exert more force in order to supply additional power. Okay, but after supplying the additional power, you see the frequency remains the same. Okay, uh, it used to be 60, and it is stable because after the disturbance, right, the frequency becomes 60 hertz again. This is reflected by the analysis of the A matrix, right? You can see that the A matrix remains unchanged with the eigenvalue of negative 1.3 plus minus J6, because this is the eigenvalue is on the open left half plane, right? Negative 1.3, and this is plus and minus, so the eigen is like this. So as long as the eigen doesn't move to the open right half plane, this is stable. Okay, this is what you learn from the eigen property. Okay, I think this is clear, right? This is should be clear. Okay, and this is the MATLAB representation. Okay, that should be clear, right? The delta U itself, when you put inside the state equation, okay, you have to somehow transform this number. Okay, delta U is equal to pi f0 divided by h times delta p. This is from the swing equation itself, right? And you put this into the state space model. Okay, and you can get the same kind of the response as well. Okay, I would encourage you to try to check the result by using this the state space equation, right? I'm not sure whether you have learned how much you have learned in your control system, right? But this is what we do in the small signal stability. So we will see you in the next video clip talking about the last disturbance. Okay, so this technique will be handled by numerical simulations or time domain simulation. We have to solve the differential equation. Okay, thank you so much.